Hello dear friends, welcome to my channels. Today's discussions, what is the commutator and the uncertainty principle. Okay, so what is the commutator? Okay, the commutator. Okay, and uncertainty uncertainty principle. Okay, so this is very important for quantum physics learner. Okay, this topic is very important for quantum physics learner. So let's start to discuss, continuing our study of operators. In this video I want to introduce arguably the most important mathematical tool when the studying observable, the commutator. Sigma x sigma p greater than equals to h bar divided by 2. Okay, uncertainty relations. If we have two operators a and b, okay, we say they commute if the action of operator ab and ba. So a b, then we can say commutator a cap b cap equals to b cap a cap. Okay, then it is commute. In other words, you can flip the two operators without any issues. In general, operators do not commute. So you can get a totally different transformation when you switch the order of the operators. However, there are times in quantum calculation that we would really like to switch there. For example, say we are looking at the product of an energy and momentum operator. We wish to act this on energy eigenvectors. Okay, so energy eigenvectors, this is my energy eigenvector. Okay, so if we could just flip their order, then we could use eigenvector property. Okay, so this is my e cap and p cap. Okay, and just flip the order, so we get p cap e cap divided by e I. Okay, and hopefully reduce the expression to a simpler one. So the reduce the expressions, it is p cap e I e I. This motivates the definition of commutator. Gives two operators A and B, their commutation is designated with the following bracket. A comma B equals to AB minus BA, and equal the following difference. So if two operators commute, then the two term on the right hand side are equal, and we get that commutations is 0. Okay, so if the commutator of two operators is 0, then it implies that they commute. How does this solve our problems? Well, in general, the commutator of two operators is equal to some third operations C. So moving A B cap minus B cap A cap equals to C cap. Okay, one of the terms in the right hand side, we see that we can flip the product so long. We also add the commutator C often times. So we get A cap B cap is equal to C cap plus B cap A cap. We also add the commutator C. Oftentimes the operator C is simple. For example, it might be proportional to the identity. So it's worth flipping A plus B, A and B. Now that is great and all, but so far this is just mathematical sleight of hand. A cap B cap is equal to K into I cap B cap A cap. Okay, so the most important tool in studying observable. Okay, so most important tool studying observables. Okay, observable, studying observable. So to being seeing why this is so important in quantum physics, let's take some time to desire an emerging property of commuting observable and their eigenbasis. Let's say A and B to physical observable. So what is the meaning of observable? Which means they both have orthonormal eigenbasis. So A cap and AB is equal to AB equals to 0. Okay, this portion, they both happens to commute. We want to analyze how an eigenvector of A relates to B. So let's take alpha to be an eigenvector of A. So alpha is my eigenvector. Okay, alpha 2 eigenvector of A can be written lambda eigenvector alpha. Okay, to see how alpha relates to observable B, we will analyze two transformations. Okay, we will analyze two transformations. To see how alpha relates to observable B, we will analyze two transformations. Okay, so first, since alpha is an eigenvector of A, so this is my eigenvector of A. Okay, So A is simply scalar it by its eigenvectors, because I have already shown that A acts on eigenvector alpha equals to lambda acts on eigenvector of alpha. So it is, when it is applicable, then it should be extended, and we get, okay, we get lambda alpha. Okay, now again on the left we will first analyze how BA acts on alpha. Okay, so where alpha is shown on the plane, so BA acts on lambda, means lambda B. So it is B cap A, BA acts on alpha equals to lambda B cap acts on alpha. So this way it is applicable. So it should be lambda so where alpha is shown on the plane. Okay, we then act with B, which takes it some places in our vector space. Okay, lambda B alpha, our vector space is lambda B alpha. The right, we will analyze how AB acts on alpha. Acting B first, it takes alpha to some direction that it to lambda alpha, since B is a linear operator. Okay, B is linear operator. Okay, see, B is a linear operator. Now we want to know how A acts on the vector X on the vector. Remember that the operators commute, so these two transformation must take alpha to the exact same place. This means we have just one choice for what A does. It has to scale the vector by lambda. So if we choose this way, and another way is this. Okay, this is the way. This is also A B alpha. Okay, I'm trying to show it in graphically. Okay, this way, in order for it to match the left side, since A on the scales B alpha, and B alpha must be eigenvalue vector of A with the same eigenvalue lambda. Now we have two cases here: non-degenerate degenerate and degenerate eigenvalues. So eigenvalues are two way. One is non-degenerate and degenerate eigenvalue. Okay, so we see that B cap alpha implies alpha. In that case, b in that case b alpha has to be the same eigenvector as alpha. Okay, so since they both have eigenvalue lambda, so we discuss non-degenerate eigenvalue. So b alpha means b act on alpha. Okay, alpha eigenvector. Okay, b alpha can only be a scaled alpha. Okay, that means b alpha equals to mu alpha. Okay, therefore alpha is an eigenvector of both a and b. So this is our first fact for commutating observable. Commutating observable. Abel's non-degenerate eigenvectors of A must also eigenvectors of B. Non-degenerate eigenvectors of A must also eigenvectors of B. Okay, so I hope it is clear that non-degenerate, what is the non-degenerate eigenvectors. Okay, next we now want to show that we can make the same conclusion in the degenerate case. Okay, which means we now have more than one eigenvectors and one for an eigenvalue, more than one eigenvectors for it. To do so, let's work in R cube dimension and assume that A has a twofold degeneracy. Okay, so my generacy is twofold degeneracy. So what happened, this is the another. So this is my two vectors. I want to show this way and this way. Okay, these eigenvectors for a degenerate, okay, twofold degeneracy, meaning there are two eigenvectors with the same eigenvalue. Okay, two eigenvectors with the same eigenvalue. These eigenvectors form a degenerate eigenspace. In this case, it is the second plane. Okay, now when A acts on any vector in this plane, it simply scales it by lambda. Okay, simple scaled by lambda. Okay, what does B do to vectors in this eigenspace? Okay, this is the questions. We actually already figured this out, so let's review what we know. Let's take alpha to be some vector in the eigenspace. Okay, now I show this is the alpha, and then let's act AB on this alpha. Okay, AB on this alpha, so acts on alpha, so AB acts on alpha eigenstates. Okay, that can be written as equals to lambda b alpha. We previously showed, so how can we explain this? Suppose act on b, then it is b at alpha, and when it is scaled, then it is mode. Lambda b alpha is the mode value. Okay, so it is scaled value. This has to equal lambda b alpha. In other words, b alpha is an eigenvector of A with eigenvalue lambda. Thus, b alpha must lie somewhere within this lambda eigenspace. Okay, and therefore must still lie on this plane. So we found an important fact: vectors inside the eigenspace stay inside when acted upon with B. Okay, what about a vectors orthogonal to the eigenspace? Okay, let's draw. Okay, no problem, I just remove all. Okay, this is my plane, you see, and now vectors acts on orthogonally. So suppose this is my vectors acts on orthogonally, that vectors is P. Okay, let P be some vector orthogonal to lambda eigenspace. We want to know what happens when B acts on P. When B acts on P, okay, B acts on P. So product with alpha, let's take the inner product. Okay, inner product alpha is inner product with alpha, which is arbitrary vector in the eigenspace. B is an observable. In here B is an observable. Okay, observable means orthonormal basis. Those who have orthonormal basis. Okay, which we proved means that B is Hermitian. Therefore, we can move it to the other side of the inner product. So alpha, we can write alpha B cap P equals to, can be written B cap alpha P. Okay, we just showed that B keeps everything inside the eigenspace. So B alpha is still within the plane and therefore orthogonal to P. Hence, the inner product between B alpha P is 0. This value is equals to 0. Okay, alpha bp is equal to 0. Since alpha is an arbitrary vector in the eigenspace, this now implies that after acting B on P, okay, it must remain orthogonal to the entire eigenspace. So B act on P. So I just, in my diagram, B act on P, just I remove and write this way, that B act on P. Okay, B act on P. Therefore, we have another fact: vectors orthogonal to the eigenspace stay orthogonal when acted with B. Well, let's take let's take some general eigenvectors of B called beta, which without less loss of generality is neither in the eigenspace nor perpendicular to it. So I draw just diagram, I change my diagram. Okay, now I show the diagram. Okay, please check, there is some different diagram. Yeah, now you see that this is B. Okay, and this way, okay, this is B and this is this. Okay, so we can decompose beta into a unique sum of component along the eigenspace and a component orthogonal to it, which we label as beta parallel and beta perpendicular respectively. So beta parallel and beta perpendicular. So we can write this way: beta parallel and beta perpendicular. Since beta is a eigenvector of B, acting B on it, it will simply scale it by eigenvalue mu. So you see that it is a beta act. Okay, beta. So B acts on beta. B acts with beta. So we can write this way: when B acts with beta, so you can write B parallel, beta parallel, and B perpendicular. We just showed that the component inside eigenspace must stay inside, and the component B on beta and scale it by mu. The only thing B can do it each component is also scale them. Okay, just I scale them. This is the scaled them. B beta 1, B beta perpendicular, this way. Next, if B did not have these properties, then B could move the two components elsewhere. But we proved that they must either stay in the eigenspace on stay orthogonal to it. So we can write B beta 1 1 equals to mu beta parallel. Okay, mu beta parallel, and B beta perpendicular equals to mu beta perpendicular. Okay, so we can take the eigenvectors of beta to lie either inside the eigenspace of A or orthogonal to it. In order for the eigenbasis of B to span the eigenspace of A. The B eigenvectors that span this space must lie with, so the space must lie within the eigenspace. Since the only other choice is to be orthogonal to the space, and then it would be impossible to span it. So we go our drawing here. So it is beta 1, it is beta 2. Okay. Since these beta eigenvectors lie inside the eigenspace of A, they must also be eigenvectors of A. Hence, we have found eigenvectors in the degenerate eigenspace that are eigenvectors of both A and B. So A and B share eigenvectors even in the degenerate case. Okay, recap. Now we discuss recapitulations. Okay, recap. A has some degenerate eigenspace, let's, and we proved that vectors in the eigenspace stay inside when acted upon within B, and vectors orthogonal to the eigenspace stay orthogonal. Next is we then use this to show that the eigenvectors of B must lie either inside the eigenspace or perpendicular to it. Therefore, in order for the eigenvectors of B to span the eigenspace of A, B must have spanning eigenvectors in this same eigenspace. Since everything in this eigenspace is an eigenvectors of A, we have found vectors. So we then used this to show that the eigenvectors of B must lie either inside the eigenspace or perpendicular to it. Therefore, in order for the eigenvectors of B to span the eigenspace of A, okay, so B must have spanning eigenvectors in the same eigenspace. Since everything in this eigenspace is an eigenvector of A, we have found vectors in this eigenspace that are eigenvectors of both A and B. Second fold degeneracy. What does this imply about commutating observable? We learned second fold degeneracy, and next questions. What does this imply commutative observable? So A, we take B and grab any eigenvectors from A's eigenbasis. If that eigenvectors is non-degenerate, then we showed that this must also be an eigenvector of B. So A1 B1. Okay, let's add this to set of shared eigenvectors. If A has degenerate eigenvectors, then we showed that there exist eigenvectors of B that also span this eigenspace. We can continue this for eigenvectors. Vectors, okay. A5 and in the end we are left with something incredible, a set of vectors that forms an eigenbasis for both A and B, a simultaneous eigenbasis. This is the truly incredible fact about commutating observable. If two observables A and B commute, then they share a simultaneous eigenbasis. Okay. Why is this important in physics? Okay. So psi, okay, psi is a momentum and collapse eigenstates P1 with P1. So P1 and P comma E equals to 0. That implies we get a eigenstate PE1. P1 E1. Quantum state would collapse into a definite eigenvectors for both momentum and energy shared with eigenbasis. In other words, our particle can be a definite state of both at the same time, and we can simultaneously know the value for momentum and energy. So suppose A and B not commute each other does not equals to 0. So you can prove that they cannot have a simultaneous eigenbasis. That means cannot have simultaneous eigenbasis. Okay, now you know that A can be written physical observable A can be written this way: summation I AI CI and okay, this way, and B can be written J AJ CJ Kate, and this way. I will show it, I will prove it in my next episode videos. Okay, then we can write observable in this form. Okay, if two operators don't commute, then there exist eigenstates of one observable that are always in superposition of the other eigenstates. Very important that two operators don't commute. That means there exist eigenstates of one observable that are always in superposition of the other eigenstates that are always superposition of the others eigenstates. Okay. So for example, if energy and momentum don't commute, then when you measure the momentum and p comma e, it does not equals to 0. So this is the example. Okay, does not equals to 0. So it is very very important for non-commutative operator. Non-commute. Non-commute means eigenstates of one observable that are always superposition of the other eigenstate. So similarly, if we say P and E, then collapse into momentum eigenstate, you can still be in energy superposition. So P11 equals to C1 E1 plus C2 E2 up to infinity. So be certain about the energy until you make a dedicated energy measurement. But when you measure energy and collapse into any energy eigenstate, you can now be in a momentum superposition and be uncertain about the momentum. You may not be able to measure both at the same time. Collapsing into the eigenstates of one can put E2 equals to C1 P1 C2 P2 this way. Okay, so into a superposition of other the fundamental connections between the commutator and a short uncertainty principle. Okay, commutator and short uncertainty principle, that is x p does not equals to 0. Okay, xp does not equals to 0. So we can write xp equals to I h bar. Okay, h bar means h divided by 2 pi. So this means that they do not share an eigenbasis. In fact, they don't share any eigenvectors. So whenever you are in a position definite state, you are always in a momentum superpositions. That is x1 eigenstate, and we get p1 p2 p3 up to superposition. Whenever you are in a momentum definite state, you are always in a position superposition. Because of their commutator, you never have a quantum state that has a definite value for both position and momentum. At the same time, they simply do not share in eigenbasis. This commutator is the root of the Heisenberg uncertainty principle. This commutator is called Heisenberg Heisenberg uncertainty. Okay, this is the Heisenberg uncertainty principle. Okay, Heisenberg uncertainty principle says that sigma x Heisenberg uncertainty principle. So sigma x into sigma y greater than equals to h bar divided by 2. So standard deviation of the possible positions times the standard deviation of possible momentum must always product of standard deviation of the possible position times the standard deviation of the possible momentum must always greater than h bar divided by 2. There does not exist a quantum state with a definite value of both position and momentum. Therefore, we can never have a certain measurement both at the same time. Generalized uncertainty principle. Okay, now I write generalized uncertainty principle, that is sigma so sigma is sigma b greater than equals to 1 by 2 I inner product a comma b. Okay, this is the another is Macon party uncertainty. Another equation is Macon party uncertainty. This is sigma square of the two uh, standard deviations. Okay, standard deviations always greater than equals to this inner product plus minus I inner product sigma psi, and this is the probability psi perpendicular. Okay, so you can get it through the Google. Okay, if you search Google, then you can get these equations from everyone. So I hope I can clear, I give some idea. So in this video is very fruitful for quantum mechanics learner. We learn operators, commutator operators, and uncertainty principle. Thanks for watching.